I'm only writing. Ripple carry adder. हाँ, full adder का नाम है ripple carry adder. Okay. क्योंकि the carry from one stage moves to the next stage. इसलिए we call it ripple carry adder also. Okay. Full adder, different types of full adders we have. Now you saw that we have, so ripple carry adder is the basic full adder circuit that you learn first. That is called ripple carry adder. Next we have carry look ahead adder, right? Where we have generate and propagate. So that carry is generated in advance. So I can speed up the process. Then you have carry save adder, where sum and carry are computed separately. So each adder needs to have a name. All of them are full adders. They're adding 3 bits at a time. Okay, so all of them are full adders. So a name is given separately to each of them. Okay, so let's start. So this is the first thing we are going to do. We already did implementation of function using 4:1 mux. It's the same function that we did yesterday. Okay, so that was using 4:1 mux. Today we will do it using 8:1 mux. Okay, so 8:1 mux means how many select lines do I need? 3 select lines. Okay, select lines will be 3. So I will take A, B, and C as my select lines. Okay. So let me just draw the K map for this particular case. Now these are my select lines. So S2, S1, S0. Okay, A, B, C represents my select lines, S2, S1, and S0. So if there are 3 select lines, I can have a total of 8 combinations for the select lines. So let me look at the Karnaugh map when my input combination is 0, 0, 0. Okay, or the select line combination is 0, 0, 0. 0, 0, 0 means AB is 0, 0 and C has to be 0, right? Yes or no? So C is 0 over here also, C is 0 over here also. So these two form the section or the two min terms where ABC is 0, 0, 0. Okay. In that you can see one is empty. One of the boxes or one of the cubes are empty. So it has only a value in this. That is corresponding to what value? What is the value there? ABC has gone as select lines. Now what is the other? I have totally 4 things. That means my circuit is now going to be a function of only D, because A, B, C are the select lines. So what is that going to be? What is the value of D in this particular box, in this particular cube? D is 1. So that means D will be the input, okay, on that line. Next case is 001. 001 combination means these two. AB is 00, C is 1. These two cubes will come in that category, yes or no? And there I have no minterm, which is true. I don't have a true minterm there. That means what is it? Is it dependent on anything? It is 0. So 0. Okay. Next case 010. 010, these two, right? 010 means A and B 01, C is 0 in these two cases. So these two cubes fall into that group. So in that case, what is the value here? No, value of D here. D bar, okay? D bar plus here D. So if I do, I get it as 1. D bar plus. So this is 1. Is that clear how it comes like that? You're supposed to group. So ABC becomes my select lines. So my output or my input values are a function of only D. And if it is only a function of D, what happens when I take each combination of ABC? Okay, which all cubes fall into that group is what we are checking for. Okay. Now, next case 011. 011. I can have these two are 011. Yes or no? AB is 01, C is 1. So 011 is these two groups. In that only one is having a true minterm, and there the value of D is 1. So it is D. Okay. Next 100. So 100, these two cubes fall into that group. So here this is the one which is, and there the value of D is 1. Again it is D. Now 101. So it is 0. Now 110. So both of them, if I combine, I will again get D bar plus D. So that is 1. Okay. The last one, these two, so it is 0. Okay. Now, if you have written down last class when we wrote for the same circuit using 4 to 1 mux, you can see that our expressions that we got were I0 was C bar D, I1 was C bar plus D, I2 was C bar D, and I3 was C bar. Okay, these were the values we got. When we implemented the same function using 4 to 1 marks, there we have two select lines and two inputs. Okay, now here the same thing when I implement using 8 is to 1 marks. This is my I0, I1, I2, I3, I4, I5, I6, and I7. So this is a more simplified way of putting it because there is no gates. I can eliminate the use of gates because if I had to do it using a 4 is to 1 marks, I needed a NOT gate to implement C bar. Then I needed an OR gate for doing this operation. I needed an AND gate for doing this operation, right? So here, if I'm implementing the same function using a higher order multiplexer like an 8 to 1 mux, I am able to eliminate the dependence on additional gates because here the inputs are either D, 0 or 1. Okay. Now, if I draw this circuit, you can either write I0, I1 ladder or 0, 1, 2 is also fine. That is. So this is how we realize the given function or any given function using mux. Okay, so depends on what is asked, whether you have to realize it using a 2 is to 1 mux, 4 is to 1 mux, or 8 is to 1 mux. Okay, beyond that we will not ask. I mean, beyond 8 is too large, so we will not ask that. But this is how. So you have to take whatever your function. If I have a function a, b, c, d, e, okay, and I am saying that I want to realize something using 8 is to 1 mux. Okay. So now, which will be my select lines if this is the function? I'm asking if this is a function. So select lines S1, S2, sorry, S2, S1, S0 is going to be A, B, C. Then how many, what is left after I use S1, S2, S0, I mean A, B, C, what is remaining here? D and E. So my inputs I0 to I7 will be a function of D and E. Okay. Of both of them in some cases, maybe a single one in some case. Okay. So that is how we have to, you have to keep that in mind. So when you get the expressions for each of them, it will be a function of whatever is remaining after utilizing the most significant ones for the select lines. Okay. Okay. Now mux tree, we already saw the implementation of a 4 is to 1 mux using smaller muxes. So that is using 2 is to 1 mux, we implemented a 4 is to 1 mux. Okay. So you have, that is called a mux tree, where you have different stages. And one thing I mentioned in each stage is that if I have 2 is to 1 muxes like this, you see I've already drawn it, is just a recap what I'm saying. Now, yes, about if it is a function of A, B, C, suppose the circuit is a function of A, B, C, then I have to use, yes, so because I'm trying to implement what this function using, it is a 4 is to 1 mux, but I'm using 2 is to 1. So 4 is to 1 is what I'm realizing actually. So 4 is to 1 has how many select lines? 2 select lines. Number of select lines is 2. So if the number of select lines is 2, I have to use A and B as the select lines. Now, where do I place B and A? Okay, that depends on, there is an order. So the priority, the one closest to the output will have the most significant variable, and the next stage will have the next one. If it is like a 3-stage case, and I say A, C might go to the one preceding it. Okay. So that's all. From the output, we start the priority. So the one closest to the output will have the most significant variable, then the next one. So, okay. Okay, now we will implement I'll show a function which we will implement using 2 is to 1 muxes. This is the same function which we implemented right now previously. This is the one. Okay, this is the same function. Okay, we are using the same function here. So you know that these are the inputs that you have to apply. So actually, now this function, if I'm going to do, it was what kind of a mux was it? If I looked earlier previously, what mux was this? This was an 8 is to 1 mux. So I'm going to implement the 8 is to 1 mux circuit using 2 is to 1. Okay. So I need to have a total of 8 inputs. Okay. 8 inputs have to be there. So, yeah. So 8 is to 1 using, it is actually 8 is to 1 using 2 is to 1. No. 2 is to 1 mux. Huh? Huh. 4, but we are questioning, yeah, it can be, but we are talking about 2 is to 1 mux. 4 is to 1 means you will have 2 of them. 2 is to 1 means you will have 2 of them. 2 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you will have 2 of them. 4 is to 1 means you if I want to implement 8 is to 1 mux using 2 4 is to 1 mux, suppose, okay, this has 4 inputs, 0, 1, 2, 3, and 2 select lines, okay, S1, S0. This also has 2 input, 3 inputs, 4 inputs, 0, 1, 2, 3, or I say this is 4, 5, 6, 7. Because the first 4 are used here. So all my inputs covered, no? I have 8 inputs. The first one, 4 is to 1 mux, will use the first 4. This one will use the next 4. Okay. And now output, how many output? Only one output. Here in this stage, I have to get only one output finally for an 8 is to 1 mux. So I have to use one more mux here. What mux will that be? 2 is to 1. So there is no symmetry in this case because I'm using 2, 4 is to 1 and then 1. You can use that also. If the question says you can use any order of mux, lower order of mux, you can have a design like this as well. Okay. So in this case, what will be the select line for this mux? A. This will have BC. Okay. And the inputs would be, if you go to the inputs, the first 4 inputs are D0, 1 and D. So D0, 1, D. Then D0, 1, 0. D0, 1, 0. So these inputs will be applied. Okay. These inputs are applied in this order. I told you how we can go backwards and check. Yesterday I was saying about how if A is equal to 0 and B is equal to 0 and C is equal to 0, what happens? So if A is equal to 0, this is the 0th input. So this line is chosen. Now this line, and I come here and B is equal to 0, B and C is 0, 0 means the first input is chosen. So D will be the output in that case. Okay. So it has to be the first input 0, 0, 0. So corresponding to whatever is 0, 0, 0, that will be the input you write here. So in fact, it comes in the same order as you have generated for a large multiplexer. That's why I wrote, even if you split it, the first 4 will go in the first multiplexer, the next 4 inputs will go into the next multiplexer if you have computed it separately. Like just from this truth table or kind of thing that we have written here, same order, you can put it on to the muxes. Okay, whichever smaller mux you have. Now, this was, so is that okay? Ketan, what is your question? Oh, that is what I just. हाँ. हो सकता है. Then it is like what we did yesterday. We had done the circuit, no? I wrote it in the first page, previous one. This will be your inputs. These 4: C bar D, C bar plus D. So what they ask you depending on that. So first you will have to have the output of a 4 to 1 mux. I mean all the input combinations for a 4 to 1 mux. Then only I can use smaller mux trees and get the thing. Okay, so the input will be this. If it is a 4 to 1 mux, what I wrote there will not be the input. Okay. That, that is what. हाँ. Here कुछ भी नहीं use करना because it is only D only, no? So I don't have to use even a single gate additionally. So this is a better design. Okay, using an 8 to 1 mux. Okay, but coming back to our question, this is not what you have to draw. This I drew just to show 4. I can use 4 is to 1 and 2 is to 1 also. 2, 4 is to 1. But your question is to use only 2 is to 1 muxes. So 2 is to 1 muxes means 2 input mux, only 2 inputs possible in one, right? 8 is to 1 means I have 8 inputs. So how many muxes should I connect to get 8 inputs? 4 of them. So I will have 4 2 input muxes in the first stage. Okay, so 4 is to, sorry, 2 is to 1. Now, since there are 4 outputs coming from them, I can use only 2 input. I cannot give it, if I could use a 4 input mux, 4 to 1 mux, I could have directly given all of them together. But my question has the restriction put that I can use only 2 input muxes, 2 is to 1 mux. So that means these two I will give to 1 mux. These two come to another mux. So this gives me the function. Okay. Now, so my what were A, B, C, D, right? Function is A, B, C, and D. So select line for this stage would be A. This would be B. All of them have C. So combination A, B, C, when it is 0, 0, 0, my input should be D. That is I0 should be chosen according to the diagram that we have here. Okay. I0 should be chosen when ABC is 0, 0, 0. So I0 is D. So now let's just work the path backwards. 1 second. So A is equal to 0, B is equal to 0, C also equal to 0. So A equal to 0 means this path is chosen. Again B equal to, so I reach here. Now B equal to 0 means this path is chosen. Now here C is equal to 0 means, yes. So whatever is I0 that will be selected. So I0 is D, which we already wrote. Okay. So that way we can write. So D 0, 1, D. Suppose if it is 1, 0, 0. Okay, A is 1 or 1, 0, 1. Let's take a different one. Suppose if it is 1, 0, 1. So 1, 0, 1 means now A is 1. Okay, I use another. A is 1 means this is the path chosen. B is 0. Okay, so I reached here, B is 0, this is 0, 1. So this path is chosen. And C is 1. C is 1 means I come through this path. So this. So this is what. So this is I0, I1, I2, I3, I4, I5. So I5 is the input that is connected to the output. All right. Okay. Same way I can have larger muxes. This is simpler mux. 32 is to 1 mux using 8 is to 1 mux I can have. So 32 is to 1 mux. So how many 8 is to 1 mux? 4 muxes I have. Okay, so 8 is to 1. We are not doing this question, I'm just showing the connection of the tree. That is it. Okay. So 8 is to 1 means I can have from I0 to I7 here, I8 to I15, I16 to I23, I24 to I31. Okay. So no. 8 inputs each. Okay, so now I have 4 outputs produced. So here what do I do? What marks can I use here? 4 is to 1. So as long as there is no restriction, you can use a 4 is to 1. And here how many select lines will I have? I have 2 select lines here. Okay, it's a function of A, B, C, D, E, F. My function. So A and B will be here. And 8 is to 1 marks will have how many? 3 select lines, right? S2, S1, S0. That will be D, D. And C, D, E. C, D, E will be the select lines for these. So this will be a function. My whatever expression is going to be a function, or the inputs I0 to I31 will be a function of what is remaining? Which variable is remaining? F. Okay, so it will be a function of F. Okay. So now, how like about we have already broken up larger muxes into smaller muxes. So what is the math behind it? Okay, so why we can do this is there is something called Shannon decomposition theorem. What it states is that if we have a function of n variables, okay, n variables like f is equal to x1, x2, it's a function of x1, x2, x3 up to xn. Okay, if I have a function of n variables, I can split this function into smaller functions. You can split or decompose, let's say, decompose the function into smaller functions with respect to one of the n variables. One of the n variables. Okay, we will do one example just to see the same thing, but how we apply what we did now. We said we will use the most significant for the outermost mux and all that. We said how when we made mux trees, but how does it work this way? Okay, so this I can write as my function x f1 x1 x2 up to xn is equal to. Suppose if I want to decompose the function into smaller parts on the basis of with respect to function x1, then I can write x1 bar function 0, x2, x3 up to xn. So I am replacing wherever x1 comes in the function with 0. Okay, plus x1 function 1, x2, x3 up to xn. Okay, so this means that x1, the first variable is chosen here, and the function is being decomposed using the first variable, giving it a value 0, giving it a value 1. Okay, this is what it is. This is the basic equation. Now let's do an example. Those who are writing, are you done with that? Yeah. Okay. So now, if f is equal to a bar b, okay. So applying the theorem, I am decomposing the function with respect to a. Okay, with respect to a. That means now my function is going to be equal to what was the equation? It was whatever the function I have to write. I'm just writing that initial thing from the previous page. X1 bar F10 X1 F11. Okay. So first I have to take the complement of the function. This is my function. So f is equal to complement of what? A. Okay. So what is it? So a bar. So a, and then I write this function by substituting the value of a with 0. A I am replacing by 0. So if a is 0, what in this function there is no a actually. There is only a bar. So a, what will be the value of if a is 0? What is a complement? 1. That means this will be, I can write this as b plus bc uh, plus c bar. Wait. No, this is a. I have written down. Okay, this is AC. Okay, there is, so this term goes off if it is A is 0 means the last term is 0. Yes or no? For this particular case. So plus when the value is A, that is when A is equal to 1 now. When A is equal to 1, what happens to A complement? A complement is 0. So this term vanishes. The other two stay. So I can write here as BC plus AC. No, not AC. AC is 1. No, A is 1. So, and it is AC bar. Okay, it is AC bar. The question itself. So it's C bar. Okay. Now what does this become? A bar. B plus BC is B, right? B plus A. So I don't have to write A here. A is 1. No? Why am I writing A? Yeah, A is there. Okay. A. BC plus C bar. What does it become? C bar plus B by absorption. Okay. So now what does this looking like? This looks like A is the select. When A is 0, B is the input. And when A is 1, B plus C bar is the input that is chosen. Can I think of it like a multiplexer itself, where A becomes the select line? So whichever one I am decomposing it with respect to, whichever variable I have used to decompose it, that becomes the select line. Okay. So this becomes A is the select line. So I can draw this as I have the multiplexer. So my select line is A, this is S. So A is the select line, and the output should be F. Inputs 0 and 1 position. 0 position, what will be the input? B, right? Because A bar means A is 0. When A is 0, B is the input. When A is 1, C bar plus B is selected. Okay. Now, I can further decompose this equation. Now, already with respect to A, I have done. But the equation has 3. This is a function of A, B, and C. Is it not? This equation is a function of 3 variables, A, B, and C. So, I initially decomposed it with respect to A. So, when I'm trying to decompose it with respect to A, what happened? I will just write this once more for those who have not understood it. Okay. So, this F is going to be equal to the complement of whichever variable I'm taking. So A complement, and I have to give A is equal to 0 in this function. Okay, in function. So substitute A is equal to 0 in the function. So I get when A is equal to 0, A bar is equal to 1. So I get B plus BC, and this is A complement. No, this is not A complement, this is just A. This time I write. So So A is 0, so this term vanishes. So this is pending. The next part is A multiplied by, you have to substitute A is equal to 1 in the function. This you have already written. I am just repeating in case it was not clear. So when A is 1, A bar becomes 0. So the first term in the function vanishes. Then I have BC plus A is 1, so C bar. Now, after getting this, you simplify using the Boolean laws that you know. You get A bar B plus A into B plus C bar. So this is same as using A as the select line. A becomes the select line. So I drew it as a multiplexer. Now that part is done. Now I can again, I'm going to decompose this function further. Okay, with respect to B now. So let me, so with respect to B, now what do I decompose? I don't have to decompose the entire function. I only take this much. Because if I want to connect a mux here, okay, B is already in the single input format. I just want to change C bar plus B because there are two variables involved there. So if I'm going to further do this with respect to B, so the same function when I use for B will be B bar, substitute B is equal to 0, I get C plus B, C is equal to 1, right? C is equal to B is equal to B, not B, 1 plus C. 1, B is equal to 1 means this is 1 plus C. Why have I put this? You people won't tell that I have put the complement outside also. Because B plus C bar, 1 plus C. Okay. Now what is 1 plus C bar? It is like saying B is my select line now because uh, I am decomposing with respect to B. So it is B complement C plus hmm, where? Ah, yeah, here. Okay, fine. B complement into C bar, correct. B complement into C bar and 1 plus C bar, right? There is a B also there. B I didn't write. So B into, let me just rub once. So with respect to B, the function becomes, function I am considering is only this much. B complement into B is 0, this becomes C complement plus B is 1. So B into, when B is 1, this becomes 1 plus C complement. Okay. 1 plus C complement is what? So B complement C complement plus B into 1. I can say. So now B is my select line. So when B is my select line, 0 and 1. When B is 0, C bar is the input. And when B is 1, 1 input. So I decomposed it further. Okay. I think explaining through Mux tree was easier than giving you explaining through this. So anyway, so this is how mathematically you can decompose the function. So here again I have multiple muxes involved. Okay. Okay. So that brings us to the end of multiplexers. Now demultiplexers. So demultiplexer is a circuit which performs the reverse operation of a multiplexer. So that means what, I will have a single input. There is only one input. I will have select lines. Suppose I am talking about a 1:4 multiplexer. Okay. And I will have 4 output lines. Okay. So a demultiplexer is a circuit with single input line, M select lines, and 2 raised to M output lines. The reverse of a multiplexer. Okay. Now, if I want to write for 1 is to 2 mux, okay, 1 is to 2 D mux. I have one input, two outputs, Y0 and Y1, and only one select line. So what will Y0 be? When will my input be driven to the line Y0? It is going to depend on my select line. When the select line has a value 0. Earlier we were saying that one input line is chosen depending on the select line value. Here, just the reverse of that, we say that one output line is chosen or goes high if my input select line is so and so. So when S bar, then the input is driven to Y0. S, if it is 1, then it is driven to Y1. Okay. So if I am to draw the circuit for this, how would it look? There are two inputs. One is a select line S and the other one is my input IN. So Y0 is going to be S bar is Y0. Then Y1. Okay, that is the circuit. Now, similarly, if I draw a 4 is to 1 is to 4 DMUX, 1 is to 4 DMUX, one input, 4 output lines Y0, Y1, Y2, Y3, and 2 select lines S1, S0. So Y0 is going to be equal to, when 0, 0, then only Y0 is chosen. Yes or no? Y1 when 0, 1 is the case. Okay, so when these two are 0, 0, Y0 is chosen, 0, 1, Y1 is chosen, 1, 0, Y2 is chosen, and 1, 1, Y3 is chosen. Okay, now usually mux and demux are found together. We have data communication for data communication. So we have a multiplexer here. I call it a 4 is to 1 mux. Here I have a demux, which is 1 is to 4. So this is at the sender end. This is at the receiver end. Okay, and I have a channel through which data is sent. So if it's a 4 is to 1 mux, I have 4 input lines and 2 select lines. So my inputs, I call them A, B, C, D. And here the demux has only one input line. So this is connected through the channel. Okay. This is your channel, communication channel. Here I have, in a demux, I have 4 output lines. So I call them X, no, P, Q, R, S. Okay, P, Q, R. So now here again I have 2 select lines, S1, S0. Now if this is 1, 0 and this is 0, 1. So if this is 1, 0, which input will be selected on the mux to be given to the output line? C. Okay. So C is selected. That comes onto the output line and it is transmitted over the transmission channel. And at the receiver end, suppose if the select combination is 0, 1, this data from the input line will be transmitted to which line? Q. Okay. Because this is position 7. So in this way, there is a communication happening between C and D. So not D, sorry, C and Q. C and Q can communicate. Okay. So they can send data maybe. So can transfer data. So this is where, so in communication, largely to transfer data, we have both these components used. At the sender end, we will have a multiplexer, and at the receiver end, we will have a demultiplexer. Okay. Now, so that's about it about demultiplexer, because it's always used in conjunction with a multiplexer in data communication. So in multiplexer, you have the larger focus is on multiplexer, how you implement different things using mux trees and so on. Okay. Next kind of combinational circuits is decoder. Okay. Now, a decoder is a combinational circuit with n inputs and 2 raised to n outputs. Okay, it can have a maximum of 2 raised to n outputs. So, depending on the combination of input that we apply, one of the output lines will be set to 1. Okay, what combination of inputs we apply? Like I have, let's look at 2 to 4 decoder. 2 to 4 decoder means I have 2 input lines and I have a total of 4 output lines. Okay. Here we do not have select lines, but we will have some other pin which we call enable that I will discuss. But 2 to 4 decoder means if I have my input as, suppose my, so this is 0, 1, 2 and 3. Okay. If my input is 1, 1. Okay. If my input combination is 1, 1, one of these lines will be active. One of my output lines will be set to 1. So which output line will be set to 1 if for the combination 1, 1 at the input and 3, right? So this will be, this line will go 1, the rest will stay as 0. Okay. So I call these inputs D1 and D0. So D1, D0, and my outputs I call them as Y0, Y1, Y2, Y3. If I'm going to write a truth table for this, I have 4 outputs, so I have to write what is the output in each of the cases. Okay. So 0, 0 combination, 0, 1, 1, 0, and 1, 1. Now when both are 0, which output will be chosen? Y0 will be chosen. So this will be 1, the rest are all 0. 0, 1, Y1 is chosen. 1, 0, Y2 is chosen. 1, 1, Y2. Okay, this is the way we will have. So, depending on the combination of inputs that we apply, one of the output lines is set to high value. Okay. Now, it is not necessary that always I have to set the output line to a high value. Okay, this kind of logic that we use, that if it is true, it becomes 1, and if it is false, we say it is 0. That is called as positive logic. Now, if you remember, we did the 7-segment display. So if I had the number 0 to be displayed, my segments were A, B, C, D, E, F, G. Since 0 like this, so only G was missing. So what did we do? We wrote 1 for everything except G, right? But if you have Googled this thing, you can see that there are 2 kinds of implementations possible. One is where this way, which we have discussed in class. Otherwise, I can give 0 value for all the active ones and 1 for the negative case. Okay. So this is also possible. This kind of a representation is called negative logic. Okay, where true is represented by 0 and false is represented by 1. But that is also, whichever kind of logic you use, finally the circuit implementation will be the same. There is not going to be any difference. So similarly, here also I can, instead of, I can represent my high with a 0. In that case, this changes to, okay, Y3 is being active means y3 will be 0, the rest will be 1. Okay, so both are possible. You can use any one of the representations. Okay, now, okay, so how do I write? Can I write each of my terms now? What is y3? Y3 is equal to, in terms of my input, what is y3? D1, D0. Okay, don't say D0, D1. D1 is my MSB. Always. So that is okay. Then y2 can be written as, y2 is 1 here. So that is D1, D0 bar. Y3 is D1 bar, D0. And not y3, sorry, y1. And y0 is D1 bar, D0 bar. Okay. So is this clear? So we have two inputs. We can have, if I have n inputs or m inputs, I can have 2 raised to m outputs maximum. And which output line? Only one of the output lines will be active at a time. And which line is active depends on what is the combination of inputs that we have applied. Okay. Now, every decoder also has one additional pin. If it's the 2 to 4 decoder itself that I'm talking about, I have an additional pin which I call G. This is my enable signal. Okay. This enable pin is going to make my decoder module active. This decoder circuit will be active only when my enable G is equal to 0. 0 means the circuit is active. G is 1. Circuit is in sleep state. Sleep or dormant state. Okay. So you do not get any output irrespective of applying inputs. If G is 1 means there is no activity happening in the circuit. I need my G to be 0 so that the circuit is active. Okay. So if I have D1, D0, 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 Y1, Y2, Y3. Now that means my output is not only dependent on the inputs, it is also dependent on the enable pin, right? Enable pin G also has to be 0 for the circuit to work. So now I can rewrite my equations as D1 bar, D0 bar, G bar. G has to be 0. Y1 is equal to D1 bar, D0, G bar. Y2 is equal to D1, D0 bar, G bar. And Y3 is equal to D1, D0. Okay. So in all of the terms that we wrote previously, we need to add G bar, which is a necessary condition for any kind of activity to take place in the circuit. Okay, circuit will be active only when G is equal to 0. So we add the G bar term to each of the expressions for the outputs that we get. Okay. So now let's see where we use a decoder. Decoder is very important. One case where we use a decoder is to select memory. Okay, specific memory. Now you have your smartphone or your laptop, so you store data in your laptop and your phones, right? So now when you store data, if I want to access something, how do I know? It has to, data is stored in specific memory location. So there is assembly language code which you are giving a name to your file and all that. So it will have a specific location where it is stored, and how does it retrieve it from that location? So how memory is like this actually. If I say in binary format, memory is an array. Okay. Like, so I have different rows and different columns. Okay. So I call this row 0, row 1, row 2, row 3. Similarly, this is column 0, column 1, column 2, and column 3. Okay. Now I want to read data, or suppose your data is stored somewhere here. Okay, this is where my data is stored. Okay, one particular value is stored in this. Each of them are called cells. They are called memory cells. Okay, each of them are called memory cells. So now if your data is stored in this, you want to read the data or you want to write data from this particular cell. What is the number of this cell? How can I call this cell? That particular cell can be called as cell num, which is a row corresponding to the cell, like you write an array. Okay, so 1 and 2, it corresponds to 1 2. Okay, so I can call it cell 1 2. So I want to address this cell 1 2, but there are so many cells. This is, even here itself we have 16 cells in what we have drawn. So how do I select a specific cell? For that purpose, I will have a row decoder here, and I have a column decoder also. So if I want to select cell 1 2, that means row 1 and column 2. So here for the row decoder, my input should be 1, right? If it is 1 means this is corresponding to R0, R1, R2, R3. Now, if it is 0 1, which line goes active? R1 goes active. So this becomes high. So this row is chosen. Row is chosen. Now, similarly, my column decoder also, I want the second row. So here the input lines I will have 1 0, no? 1 0, 1 0. Okay, 1 0. And then my output I have C1, C0, C1, C2, and C3. 1 0 means this line will be 1, the rest are all 0. So this column will be chosen. So corresponding to that particular row and column, that particular cell can be accessed. So I can write data into that cell. I can even read the content of the cell. Okay, that is how bit by bit. This is like in one cell, only one bit will be stored, 1 or 0, like that. Okay, we are not talking about data the way you write, but this is how we access memory. So memory is an array where we have multiple cells. Now, so it's in a row column format. To access a specific memory cell, I have a row decoder and a column decoder, which helps me to, get data or to write data into a specific cell. Okay, so this is one major application of decoder. Okay, then second application is we use it to activate one of the many modules. Example, suppose I have a decoder here, which is a 2 to 4 decoder. Two inputs, four output lines. Now this can be connected to the enable of this one, this output. This can be connected to the enable of this one. These are all other decoders, 2 to 4 itself, let's say. So in this manner, suppose what happens, I am using negative logic and I'm saying that when it is 0 0, this becomes 0, rest all are 1. Okay, I'm using negative logic here. So which line is active becomes 0. Suppose I'm saying, okay. So my input combination is 0 0. So Y0 should be active. Active is represented by 0. The rest of the lines are 1. Okay. Now if this becomes 0 means what happens? This is connected to the enable of this particular decoder. So this becomes active. Okay. So but the rest of the modules will be in sleep state. Yes or no? Because these are all one. The rest of these modules will not be active. They won't be enabled because I need a 0 value to enable each decoder. So in this way, I can specifically activate one of the many sub-circuits or modules, as I can call it. Okay. So that is another application of decoders. Okay. Okay. So constructing a 4 to 16 decoder using a 2 to 4 using 2 to 4 decoders. Okay. This is exactly the opposite of mux tree. In mux tree, what I had in mux, I had that initially I had a large number of muxes. Then as I approach the output, I will have only a single mux. Is it not? Here it is just the opposite. We start with a single decoder and we branch out into many. So the opposite is how a tree mechanism works in decoders. So I'll just show that. Okay. So I am saying that this is a function of A, B, C, D. Okay. I'm saying that what I'm implementing my whatever function that is. So I have a 2 to 4 decoder here. What did we do? We had select lines in mux and we gave the most significant select lines to the ones closer to the mux closest to the output. Here again, it's the opposite. So I will give the most significant variables to the inputs. Here I don't have select lines. So the inputs connected to the first stage. So A, B will be the input here. Okay. And I have a G. So I have 4 outputs. Now, if I'm using the normal logic, that is a signal goes high, okay, and I have 4 decoders here. Two, three, four. So if this is one, I cannot directly connect it to G. I'm saying the normal case, so I have to give inverter after each other. Is it not? If I want to activate these modules, these are going to be used to activate. What is the confusion there? Why so much of noise? Janil and yellow t-shirt, what is your name? Raj, you are Raj. Okay. Okay, fine. So now here, each of them have 2 inputs. Now these inputs are going to be C and D. The next 2 inputs will be given, variables will be given as inputs. Okay. So the output of the first decoder is going to activate one of these decoder modules in the second stage. And each of them have 4 outputs, Y0 up to Y3 here. I am drawing dot. That doesn't mean you draw dot. Okay, for exam or in your record. Okay, notebook you draw, I don't mind. But when you're writing something officially, you should be having it. Okay. So now let's take the case A, B, C, D. Okay. Now if A, B is 0, 0 and C, D is also 0, 0. So I was trying to construct what? I was trying to construct a 4 to 16 decoder. That means I should have a total of 4 inputs. So 2 inputs are applied in the first stage. The next 2 inputs are applied in the second stage. And how many outputs I have from Y0 to Y15? That means I have 16 outputs now. I have completed the design of the decoder. Okay, using 2 to 4 decoders. Now, here, if A, B, C, D is 0, 0, what happens? 0, 0 means which input will go, which output line will go active? First one. Okay. If first one goes active, which decoder will be activated? First one. So this is activated. And what is the value of C? CD is 0, 0. According to the combination I've written here. Okay. So I will have 16 combinations, as you know, because A, B, C, D can take values from 0, 0, 0, 0 to 1, 1, 1, 1. So which is the output which will go high? Y0. So in this case, if I have, I will write. So A, B, C, D, if it is 0, 0, 0, 0, I have outputs from Y15, Y14, Y13, 12, 11, up to 2, 1, 0. I'm only writing that much. Yes. Inverter goes 0, right? If what is G supposed to be to activate a decoder? What is the value of G? G should be 0. Only then the module is activated. So since the design is like that, if this is 1 and it comes, if any of them turn 1 also, nothing is going to be activated. None of my decoder blocks in the next stage is activated. So I have to invert it after that. Or else I have to use the other logic, reverse logic that I told, that if it is an active state, I represent it by a 0 and the other states by 1. In that case, you will not have to use an inverter. Okay. So here, what was I saying? So Y0 is 1. No, when it is 0, 0, 0, 0, Y0 is 1. The rest are all going to be 0. Okay, only 1. Now, if it is 0, 0, not 0, 0, 1, let me take another case. Okay. 0, 1, 0, 1. Suppose. Okay. 0, 1, 0, 1 means I change the values here. This is 0 and this is 1. That means which output will be 1? The second one. 0, 1, 2. This one. Right? Why 5? AB is 0, 1. I am still in the first decoder. Oh yeah, line number 1. Sorry. Line number 1. The rest are all 0. Okay. So line number 1 becomes active. So which is the decoder in the next stage which will turn on? This one. Okay, the second one turns on. Second one turns on, and what is the value of CD? 0, 1. So Y5 will be 1. So I have not written. Wherever Wi-Fi is there, that will be 1. And do you want me to throw you out of class? Anyway, only 5 minutes, so I'm not going to throw. Today I didn't have time. So, Mr. Vraj, I'm talking to you only. Okay. Then one more case, 1, 0, 1, 1. Okay, 1, 0, 1, 1 means 1 and 0. So this will become 1. The rest are all 0. So this one turns on, and 1, 1 means Y11 becomes 1. Okay. So this way, one of the lines will be activated. So the output of the first decoder is used basically to enable the rest of the decoders in the second stage. Okay. It does not provide us any output lines. Output lines all come from the second stage of decoder. Okay. One more thing. Any logic function can be realized using decoders. 0, 3, 4, 6, 7. How we can realize using a decoder is that, suppose here I have 3 variables representing the function. So I should have what kind of a decoder? The decoder should have 3 inputs. So I will use a 3 to 8 decoder. Okay, 3 to 8 decoder. So if this is my decoder block, 3 to 8. So here I have inputs A, B, and C. I have 8 outputs: 0, 1, 2, 3, 4, 5, and 7. So now I can use a decoder followed by an OR gate. Okay, followed by an OR gate. Why OR gate? Because the function is going to have a value 1 in any of these minterms. Now, if these are the true minterms, 0, 3, 4, 6, and 7 are the true minterms. So if any of these terms are true, my output will be 1. So I can use a OR gate to combine the inputs. So from 0 I give here. Okay, so this will be my function. Because if I'm going to write it as an expansion from this minterm equation that I have given, so it is going to be a bar, b bar, c bar plus, you will write like that. The same thing, all those minterms only I'm adding here. So OR is for, so any function given to you as a minterm, let's see, another one, f small one only. So there is not much confusion in implementing 1, 4, 5, and 6. Okay. Again, 3 inputs means I have to use a 3 to 8 decoder. Zero, 1, 2, 3. One, 4, that gives me the function. So this is the basic implementation. So now we have to learn some special decoder designs that we will not do today. We will do after your exams. So all the best. Prepare well. Read questions carefully. Two input gates means two inputs, not two gates only. Okay, these kind of silly questions you people come up with. So usually nobody puts a limitation on the number of gates that you can use. We say about the number of inputs to the gate. Because we have this fan in, fan out problems, we always have a limit on the number of inputs, not on how many gates you can use. The lesser number of gates, the more optimized your design is. That is there. But number is never specified. How many gates? Okay. Thank you. You can leave.